Hello guys and welcome back. So now we're going to fix the issue where with this orientation, and the first thing that we want to do is with the bound geometry we are using point number 0 in this case, and for in this example point number 0 is going to have, this is its first neighbor and this is its second neighbor. So none of these two vectors are important to us because we want to know which one of these guys is the longest. Okay, we want to use one of the longest pieces, either this, or this, or this. Okay, and if we end up using a face, this face, it's not going to give us the correct information that we need. So we have to isolate first the longest piece of geometry from this guy, and we can do that using a measure sop. So we're going to measure the area of each primitive, and then we're going to keep the longest one. And a very simple way to do this is to sort the primitives. So if we take a look at the number of primitives, this is 0, 1, 2, 3. We can go and say, okay, we're going to use the primitive number 1. It will work in this example, but as the geometry changes, the primitive number 1 is not going to be the same. It's not constant. So we're going to sort the primitives using the measure attribute, okay, the area attribute. And now you can see it's giving us, this is the smallest one and 5 is the longest one. We're going to inverse that. Okay, so 0 is going to be the biggest one, and the higher, the smaller the area. Now we can safely isolate the primitive number 0. Okay, so now we have primitive number 0, it's this guy, and then we can say, okay, we have point 0, it's constant, each primitive has point number 0. The first point is going to be this, and the second point is going to be this. Now from these two guys we have to figure out which one is the longest. Okay, so let's do that. We can keep that. So we're going to create two vectors. I'm going to call this long and short. Okay, and then we're going to measure the distance. So this guy, we're going to first measure the length of the first vector and compare that with the length of the second vector. So we have, this is our first vector, and let's call this vector A. Actually, yeah, we can do that. So vector A is going to be position 1 minus 0, and vector B is going to be position 2 minus position 0. And then we're going to say if the length of A is bigger than the length of B, then A is the longest one. Okay, in that case we're going to assign long equal to A, and then short is equal to B. Else, if that's not true, then it's the inverse. So the long one is A, the long one is B, and the short one is A. And I don't need these guys. I'm gonna just export an up vector, which is equal to the longest. So long is equal up, and then I'm going to export just another axis, which is the other one basically. So we're going to get this, and then the other axis, which is this guy. We can call this z-axis, and this is going to be equal to the short axis. Pardon me. I'm not going to compute the up here. I will do it inside the point VOP, and we're going to normalize these two guys. Okay, let me double check. So we are getting point number 0. We're importing the position of this guy. We're importing the position of the first neighbor and the second neighbor. We're computing a vector that travels from point 1 to point 0 and from point 2 to point 1, and then we're computing the length of the first vector, so that's A, and against the length of B. So if A, the length of A is longer than B, it means A is the longest and B is the shortest. If that's not true, then B is the longest and A is the shortest. So that's what the if statement here. We're doing the comparison and we're assigning long to A and short to B, or the inverse of that. And I'm exporting up and Z axis. So let's dive inside. Let's rename these guys. So I only need the up and the Z axis. And I'm going to do the cross product here to get the 2 vector. So that's going to be up and Z, and that's our 2 vector, and the up is our up vector. And let's go up, and we're applying the transformation, and now it's aligned properly, and there we go. It's working. So now we can do the Voronoi fracture that we did here at this space. So okay, and let's apply the inverse of that. Invert transformation. Okay, that's a decent amount. And then we're going to apply the inverse of transformation. So I'm going to copy this node, and we need to transform this back, so we simply invert the full transform. And our geometry is back into space. And now it's looping over all the primitives. And there we go. We have our wood fracturing pattern. And I'm going to add a compile block that's going to speed up the process drastically. So let's do that. We don't have anything complex here. So compile block. This guy, and then this, and this is our output, and we're going to tick on enable multi-threading when compiled. Let me check one more thing. Yeah, everything's good. Okay. Yep. See the speed. That's what I was looking for. So let me change this to 210. And see how fast it was. It's done now. If I look at if I do it here, if I evaluate this node without the compile block, see how long it takes for this to cook, and it's still going. If we use the compile block, it's going to use all the threads and spawn each copy of the geometry into a separate thread. So that's how long it took to cook this geometry. And then if we look at the compile block, it's done. So it's a huge amount of speed gain there. And that's pretty much it. We bound the geometry using this guy. We measure it, find the longest piece, and then from there we build 2 vectors, this one and this one. We find the longest one, that's going to be our up vector, which is the long here, and then the other one is going to be the z-axis, which is the shortest one. We can name it anything really. And then from there we compute the cross product. That's going to give us a vector pointing this way. Okay, and those are going to be that's going to be our 2 vector, and then the up vector here. This is our up vector, and the transform is the difference between point 0 and the origin, so that's our translate matrix. And then this is our rotation matrix, and then we invert all of that, multiply it to the point position, and that's going to give us back this. We then copy this transformation back into the original geometry. We scale it down, we Voronoi it, and then scale it back. And that's our result. Let's do an exploded view that's the geometry. Let me assemble it, and yeah, it's fine. So that's our geo, and in the next video we're going to start setting up the constraint system. Thank you for watching, and see you in a bit.